Okay, I'll just take you through the design considerations now. Have a look at this first. We'll start off with our disc again. Here it's in the dark. It rotates to the 12 o'clock position and the light flashes on. But in this case the light stays on, and it stays on, and it stays on, and it stays on, and the tab that we see is not a clear sharp image, but it's stretched out blurry thing, and it eventually goes dark again. So the effect you get is this. So in this top image we see a 10-degree rotation of the disc, and that's the light being switched on for a period of 10 degrees and then off for 350 degrees. This is the preferred scenario where the light is on for 1 degree and it's a much shorter pulse, off for longer. Although in actual fact the AT-Tiny85 has a 10-bit register for the timing, and whatever time it develops has to be divided by 360, and it turns out that because it has 8-bit registers which will count up to 256, it's much easier to divide by 256 than it is to divide by 360, so I opted for that. In actual fact it doesn't make very much difference to the rotation. Dividing by 360 gives you 1 degree, and dividing by 256 gives you 1.4 degrees, and when you actually examine it in reality it's still very acceptable. So what we want is to generate a waveform like this with a pulse that switches the light on but it's off for most of the time, and I wanted the stroboscope to be able to effectively stop a rotating object that was rotating from 120 revs per minute, which is 2 revs per second, which is pretty slow, up to 12,000 revs per minute, which is 200 revs per second. At 120 RPM, that's one flash every 500 milliseconds, which is half a second, and the flash duration is that 500 milliseconds divided by 256. It comes to 1.95 milliseconds. At 12,000 RPM, that's one flash every 5 milliseconds, or 5,000 microseconds, and if you divide that by 256, it gives you 19.53 microseconds for the duration of the pulse. Now the AT-Tiny85 has 2 timers in it, so I've used one of them to generate the time base for a pseudo timer which I use for counting the length of this delay. The other timer I use for counting the duration of this pulse. This dark line here is the waveform that we want to produce. At its slowest there's 500 milliseconds between pulses. Keep that figure in mind. Inside the AT-Tiny85 there is an analog to digital converter which I'll refer to as the ADC from now on, and we're going to use it to read a potentiometer which is connected from plus 5 volts down to ground. So that's going to give us a reading according to where we set this, and the reading is a 10-bit reading that comes out of the ADC. 10 bits can count from 0 up to 1023. Now 1023 is just a little bit more than 1,000. The distance between these two pulses is 500, so there's a handy ratio there. So if we count up a half milliseconds, there will be 1,000 half milliseconds in between these two pulses. If we use the value from the ADC as this line here, which is the limit to which the pseudo timer must count in the allotted period, then at its slowest, when the pot is set right down, it will count up to 1,000 in 500 milliseconds. In order to do that, it must be incremented once every half a millisecond. We're going to use a couple of registers, R18 and R19, as a pseudo timer, because all of the native timers in the chip are much too fast for this. So this is a pseudo timer that we're going to make ourselves with R18 and R19, and they're going to count up according to this blue line here, and they have to count from 0 up to 1000 in 500 milliseconds. So these two registers have to be incremented at a rate of 1 every half a millisecond. When this waveform here is running at a much higher speed to stop a much faster rotating disk, the distance between the pulses is much shorter, and the pulse length itself is much less as well. And I've drawn a representation of that down here. These pulses here, that's this running at a higher speed. Now, the way we make it run at a higher speed is we move this pot. So it might be down there, let's say. And the value that comes out of here is different, so that this line here will be in a different place. And if I set it down there, here's the value from the pot. And now this blue line counts up and it reaches that value at a much faster rate. So now here's our faster rate pulse waveform that we're making, and we've done it by changing the pot so that this line here, this is the value of the pot that was being used before for 500 milliseconds. It's now down here, and the same line, it counts up at the same rate, but it gets up to a value, it gets up to the value of the pot in a much shorter time, and then gets reset and counts up to the value of the pot again. So, and every time it resets, it will be used to form one of these pulses. So that by changing this line, the value from the pot, by turning the pot, you change this line, and you can change it from 500 milliseconds down to something much less, and in fact you can take it down to 5 milliseconds, which is the highest speed we need. Well, that's all very well and good, but this line here, this is the counter contained in R18 and R19, and they need to be clocked twice every millisecond. So where does this half millisecond pulse come from? Well, inside the chip there are two timers, and timer 1 is the one displayed here. The chip has a native clock speed of 8 megahertz, but in all of the projects I've ever done, I divide that down by 8, so I get a clock speed of 1 megahertz, and that gets distributed to all the peripherals. Both timers have prescalers, which can divide the 1 megahertz clock down to a lower frequency, and in this case I divide it by 2, so that instead of a clock every microsecond, I get a clock every 2 microseconds. Timer 1 is given a limit count in OCR1A, in the output compare register 1A, of 250. That's this line here. That's a limit set at 250. So the counter counts up to 250, and then it is set so that it will reset itself. You can do all sorts of things with the internal timers, which you already know if you followed the previous course on assembly programming on the ATtiny85. There are all sorts of things you can do with the timers, and timer 1 is set so that it will increment up to a value in its output compare register, which in this case is the value given it by the ADC, and at that point it will reset, and at the same time trigger timer 2, which will give the duration of the light pulse. So what we need to do now is talk about timer 0. I said timer 2 before, I meant timer 0. Because we have a value of 10 bits coming out of the ADC, we have to divide this down into a register of 8 bits in order to handle it for what we need to do. So I divide it by 4 by right shifting it twice. That shifts everything out of the the upper 2 bits and everything is done in the lower 2 bits, and we do lose the 2 lowest bits off here, but they are the lowest bits. I mean, they have a maximum value of 3, so it's no really huge loss. Once we have the pot value divided by 4 into this register here, which is the pulse length, register 22, I suggest that you stop the video at this point and just read through the notes here, because they do describe it, I think, fairly fully. And they also give this bottom one gives a method for testing it in the code. It starts off by saying, right, let's just read this one thing. Look for ADC complete. This is in the code, so look for that string. It's in an interrupt. It would load the ADC value into pot val, but the code is not connected to any pot. Obviously, it's just a code in a simulator, and there is no physical analog to digital converter. So replace these loads with your own pot valve, and it. I've given a couple of suggestions here. 01 Fox4, which gives a value of 500 decimal. Now search for SBI port B0, PB0, and set a breakpoint against it, and also search for this and set a breakpoint against that, and then just follow the method and you will find that it works. The only reason that I wanted to bring this to your attention is, remember that you set this in here, these two things, so don't forget to take them out again before you program your chip. Okay then folks, I think that's about it. I think that just about describes the value of the operation of the strobe, and I hope that somebody built it maybe, or at least goes through the code and appreciates how it works, and maybe just learned something about programming the ATtiny85, because this does use all 3 of the major peripherals, both timers and the analog to digital converter. There are a few other things in the chip that I haven't used, but well, they're not awfully complicated, and with this and with the general information that you were given in the previous course, you're set to do anything. The world's your oyster.